SwayamPrabha. Digital India. Educated India.
Welcome to the DTH sponsored course on micromachining. These are some of the micro products that are made with the help of micromachining processes. Today I am going to talk about micro nano abrasive finishing technologies. An overview. I will mainly discuss magnetic abrasive finishing (MAF) and magnetorheological finishing. I repeat that some of the slides shown in introductory lecture may get repeated over here, so please bear with it, but the references are different. What we have done in the last lecture: glimpses of work done at IIT Kanpur on nano finishing technologies, acknowledgement and related books of the speaker, what is micromachining, advanced abrasive micromachining finishing processes and their classification. This lecture deals with magnetic abrasive finishing, some issues related to magnetic abrasive finishing process, magnetic abrasive nano micro deburring. I have discussed this in another lecture also while dealing with electrochemical micromachining little bit. Nano finishing of free form surfaces, a challenging task. Magnetorheological finishing, very important process. It was developed by QED company of USA, America. And how to enhance the performance of abrasive flow finishing process, and the conclusion that will be discussed after this. And then here we will discuss the conclusions overall of the talk. Acknowledgement, I will quickly go through it. All those who have contributed to nano finishing research work at IIT K, they are acknowledged here: Dr. R.K. Jain, Dr. Sunil Jha, Dr. Vijay Gorana, Dr. D.K. Singh, Dr. S.C. Jaiswal, Dr. Manas Das, Dr. Ravi Shankar, Dr. Ajay M. Sitwara, Mr. Prabhat Ranjan, rather Dr. Prabhat Ranjan, Mr. Pavan Basera, Mr. Satish Kumar, Mr. Mithun Sarkar, and a book on nano finishing science and technology can help and give you most of the information that I am going to tell you in the following 3 lectures. Today's lecture and following 2 or 3 more lectures on nano finishing technologies. Now while working, these people were working, they were making use of different sponsored projects. BARC Tombe Mumbai, DST sponsored project New Delhi, ARDV Bangalore, CSIR New Delhi. Sorry for the repetition, I have already mentioned to you. Magnetic abrasive finishing. Applications of this particular process are for flat cylindrical workpieces, internal and external surfaces, and nano finishing, and it is also used for deburring processes or deburring work. We are going to discuss design and development, including fabrication of the magnetic abrasive finishing process production machine tool that was also done at CMTI Bangalore in collaboration with IIT Kanpur. Magnetic abrasive finishing, this setup was developed under the project of DST. Now you can see here, this is a simple vertical drilling machine which has been converted into magnetic abrasive finishing machine. Here you have the medium which consists of magnetic particles, that may be iron particles or CIPs, and abrasive particles. And you can see here, this is the flexible magnetic abrasive brush, FMAP. Flexible because it will adapt the shape, whatever is the shape of the workpiece, it will adapt it to itself. So that's why it is known as flexible magnetic abrasive brush. And when you are rotating this brush, then abrasive particles come in contact with the workpiece surface over here, and peaks or irregularities of the workpiece surface are sheared off, and you get a very good surface finish. You can see here, this is the surface texture or surface plot before magnetic abrasive finishing process. Here the RA value is 0.51 micrometer. This is after MAF. You can clearly see the difference in the 2D plot of workpiece surface before and after, and here the surface finish has come down to 0.16 micrometer RA, and further finished, then it has come down to 0.11 micrometer RA value. So we can clearly see the big difference between the surface finish before MAF and after MAF. We will discuss some more details. Now this is the direct current MAF. Now because if electromagnets are used, you can have the direct current or you have the pulsating current. We will see pulsating current has been proved to be more efficient, more accurate than direct current. We will see it later. This was designed and fabricated at IIT Kanpur. Best surface roughness achieved by the students at IIT Kanpur was 40 nanometer, but it can be further reduced if proper optimization of the workpiece and other machining parameters, not the workpiece really speaking, machining parameter optimization is done. Schematic view of MAF working principle. Working gap, that is the gap between the bottom face of the tool and top face of the workpiece surface to be finished. It is filled with magnetic abrasive particles, form flexible magnetic abrasive brush that we have seen in the earlier slide. Flexible magnetic abrasive brush is having multi-point, many cutting points are there. So each cutting point or each abrasive particle can be treated as a tool. So you can see over here, this is the north pole, this is the south pole, and above this there is a workpiece, and this is the flexible magnetic abrasive brush. When you are rotating this flexible magnetic abrasive brush, abrasive particles finish the surface of the workpiece, because each abrasive particle acts as a tool if it is in contact with the workpiece surface, and you can give the feed to the workpiece surface in this direction as well as in this direction. So whole surface is being covered over there. This is the enlarged view. You have the magnetic abrasive particles over here, and this is the flexible magnetic abrasive brush. Now one thing you can note down, that you can have the loose abrasive particles and CIPs, carbonyl iron particles, or you can have a sintered magnetic abrasive particles. Sintering has been done, and you have very fine sintered magnetic abrasive particles. Their performance is definitely better than the loose abrasive and CIPs. Now please see it, this can be easily applied for the flat surfaces. It can also easily be applied for the cylindrical surfaces. This is the cylinder to be finished. You can see here, this is the magnetic abrasive particles. They may be sintered or loose magnetic abrasive particles, and here is the slot on the south pole as well as north pole of the magnet, and these slots are deliberately made, because so that here the concentration of the magnetic field will be there, and if concentration of the magnetic field is there, higher forces will be acting on the abrasive particles to penetrate inside the workpiece. So you will have higher material removal rate. Please note it carefully. I have already mentioned in other lectures that material removal rate and surface finish, they are directly proportional. Higher the material removal rate, higher is the value of the surface finish, that is poor surface finish. So you can clearly see the mechanism of material removal. This is the peak of the surface to be sheared off, and here is the normal magnetic force that is acting on the abrasive particle. This is the abrasive particle, and there is the cutting force in this particular direction. So whatever is the penetration, that much material, penetrated material is removed as the microchip, and that is what is done over here as well as here, and that's why you get such a good surface finish on the machined workpiece, and this is the peak on the workpiece surface. Salient features are a surface value that as good as 8 nanometer surface roughness value was achieved at other places, especially Professor Ranga Komandri, who worked in USA. He achieved 8 nanometer as the best surface finish. As I mentioned earlier, they can be improved further by optimizing the process parameter. Comparison of surface produced by static flexible magnetic abrasive brush and pulsating flexible magnetic abrasive brush. Static means DC is used, pulsating means pulsating power is used, and flexible magnetic abrasive brush is itself breaking and making during the process. So you can see here layers obtained with static flexible magnetic abrasive brush. This is the surface texture and 3D SEM photograph. Time taken in FMAP is 4 times more than the time taken by pulsating flexible magnetic abrasive brush. So pulsating flexible magnetic abrasive brush is giving better time, better performance, and more efficient. It takes lesser time. Now you can see here still grinding marks are there. This is the lathe obtained by pulsating flexible magnetic abrasive brush. These are the left grinding marks. Here there are many deep grinding marks, but here also some grinding marks are left. So all this will depend upon how long you finish the workpiece. Pulsating flexible magnetic abrasive finishing. This was done for 15 minutes and this was done for 45 minutes. Now lathe obtained by pulsating flexible magnetic abrasive brush. This is the lathe obtained by this brush, and you can clearly see here. Here T on is 2 milliseconds. No grinding marks are there, but pulsating flexible magnetic abrasive brush grinding marks are there, which are visible over here. So this way you can finish the surface to a very good surface roughness value. Problems associated at very low duty cycle, 0.08 duty cycle is there because you are using the pulsating current. So you can clearly see here this kind of the pit is formed. The question is why this pit is there. I will show you, because the forces that are acting at low duty cycle are very high. We will see the figure. This is again there. Again here crack has taken place at low duty cycle 0.08. This is also 0.08 because such cracks are not acceptable and not desirable. So here the duty cycle is 0.16, but still some scratches are there on the machined surface. Now this is the 0.24. Here cracks are not fractured, surface is not fractured, deep scratches are not there, so it gives slightly better. So what it simply means is that you must optimize the duty cycle also, and it depends upon finishing parameter, workpiece surface as well, and definitely whatever is the pulsating, whatever is that brush constituents, they have to be optimized. Gap kept is around 1.5 millimeter, RPM 200, and finishing time 15 minutes in this particular case. Comparison of force, as I mentioned to you in the earlier slide, that you can see here at very low duty cycle forces are very high. You can see this goes up to 3000 Newton, while if you are using the DC, forces are very low. So due to high current ratio, you get these kind of the, this is the normal force Fmn. Now this is with static flexible magnetic abrasive brush. You can see it is around 70. So comparatively forces are very low, and this is the cutting force, and this is the normal, this is the normal force, this is the cutting force. Here this is the cutting force and this is the normal force. Some issues related to magnetic abrasive finishing process. Pulsating current in MAF, why one should use DC power supply? Can we improve performance of MAF process by using pulse DC? I have already shown to you that yes, you can improve the surface, you can improve the performance by using pulsating direct current, but you have to optimize the parameters. Critical surface finish. With increase in number of finishing cycles, surface roughness value keeps on decreasing. That means surface finish keeps on improving and attains asymptotic value. That means you keep finishing it, but RA value does not change. Why? That is the question which I have raised over here. Then rotation of the abrasives, will it improve the performance or not? With increase in current to the electromagnet, because in some cases you can use the permanent magnet, but mostly it is the electromagnet which you can control. Magnetic flux you can control in electromagnet externally. Percent change in RA value keeps on increasing, attains an optimum value and then it starts decreasing. Why slots in the electromagnet are used? I have already explained this particular part to you. Electromagnet has a slot along its periphery. I have already told you that because of the higher flux density at the discontinuity, these slots are used and they help in reducing the finishing time. What is the optimum number of slots? That is again a question, and which should be solved by the researcher or the user by theoretically as well as experimentally. Acknowledgement, I have already told you this acknowledgement. Most of the researchers are using a smooth DC power supply resulting in low finishing rate, because I have shown to you the time taken by DC power supply, magnetic abrasive finishing and pulse power supply, magnetic abrasive finishing, and comparatively higher RA value of the finished surface is obtained. Pulsating current in MAF, why one should use DC power supply? Can we improve performance of MAF process by using pulsed DC power supply? Solution: yes, pulsed DC power supply is going to give you better performance and better surface texture. Methods of energizing flexible magnetic abrasive brush. You can use DC MAF, direct current magnetic abrasive finishing, pulsating current magnetic abrasive finishing. When you are using DC MAF, the flexible magnetic abrasive brush is known as static SFMAF, and if you are using pulsating current, then it is known as pulsating flexible magnetic abrasive brush. Surface is produced by surface grinding and static flexible magnetic abrasive brush. You can see here reduction. This is the kind of lathe obtained by the grinding surface and lathe obtained by the static flexible magnetic abrasive brush. Here also you can see irregularities on the finished surface. Here there are large irregularities. Here still there are certain small height, but they still exist due to abrasive particles held more strongly. This kind of the surface is obtained. DC magnetic abrasive finishing without feed rate, and this is the DC MAF with feed rate. So feed rate also affect whether you are giving the feed to the workpiece or not. That also affect the final texture of the surface that is being obtained. comparatively uniform as compared to this case, where you are not giving the feed or feed rate is 0. Formation and partial breaking of FMF, this is very important to understand. Now you can see over here, this is the time, this is the pulse current. This is the pulse current, then you can see this is increasing, then this is on time, this is off time, on time, off time. Now you can see here, during the on time, brush is being formed, flexible magnetic abrasive brush is being formed. This is the north pole, this is the south pole, and this brush is being formed. When it is rotating and feed is given to the workpiece in this particular direction or in this direction, then finishing takes place. Here it is off time, so you can clearly see the brush has broken down and it has become very thin because of partial magnetic field is there. That's why this kind of shape is still there, remaining there in the off time, that is given over here, and you will not get efficient finishing in this case. But when on time is there, brush is formed and it is able to finish the workpiece. So this is what is moving either this direction or in this direction. So formation of FMF during on time and partial breaking, falling of FMF during off time. With increase in number of finishing cycle, surface roughness value RA keeps decreasing and attains an asymptotic nature. Why? You can see here, with finishing time, this is the simulated surface roughness value, this is the surface roughness Rmax in micrometer, and this is the experimental surface roughness value, or both of them are meeting at certain point of time. So but both of them indicate that surface roughness value is decreasing with finishing time. That means surface finish is improving. Based on micromachining conditions, critical surface roughness value keeps repeating. So this is the critical surface roughness value because it is not going to change beyond this particular point. If it is not going to change beyond this particular point, even if you keep finishing, then that is known as critical surface roughness value. Some variation in the roughness value will be there because magnetic abrasive particles mixture carry a range of abrasive particle size. Now, because this mixture carries small and large size abrasive particles, which will definitely affect to some extent. So some fluctuation may be there along the time, but practically there is no substantial change in surface roughness value with time after critical surface roughness has been attained. This is asymptotic, as you can see here, beyond this particular point. So critical surface roughness value. Now how it is going to work? Stages in material removal from individual irregularity. This is the individual irregularity. This is the abrasive particle, and these are this is the abrasive particle, and these are the iron particles or CIPs as shown over here. So these are holding the abrasive particles, and depending upon the forces or the forces with which they are holding the abrasive particles, it will move downward as well as shear off this particular peak. As you can see here, this peak has been sheared off, and this is the removed material in the form of microchip or nanochip, depending upon what force is acting on this abrasive particle, and it has been separated out. So how it works is more clearly shown over here. These are the irregularities. This is the abrasive particle removing the peaks from the surface. Some small size abrasive particles, they get entangled within the valleys of the machined surface. So selection of the abrasive particle is also important, and you can see it has sheared off and it is further improving the surface, and finally you get this as the critical surface roughness on the workpiece, and this is the vertical cross section of this surface is something like this. So you can see how this critical surface is produced. This model is applicable to MAF, AFF, that is abrasive flow finishing, as well as magneto-rheological abrasive flow finishing processes. Issue number 3, rotation of the abrasives with increase in current to the electromagnet or magnetic flux density, percent change in Ra value keeps increasing and attains an optimum value, and then it starts decreasing. This is what I have shown to you earlier also. Rotation of abrasive particles takes place when, what will happen if Fmn, that is normal force that is acting on the workpiece surface through the abrasive particle, which is responsible for penetration of the abrasive particle into the workpiece, is increased to a high value. Very large depth of penetration will be obtained, and when Fc, that is the cutting force or the shearing force, is not increased proportionately according to this Fmn, what will happen? It depends on many factors like medium strength, magnetic field strength, motor power, etc. Now, if Fmn is very large, it will penetrate inside deeper, but if this Fc is not enough, then it will not be able to remove the whole material as the chip like this. If it penetrates up to this point and this Fc is smaller, then whole of this material will not be sheared off because Fc is not sufficient. So, pulsed DC power supply, you can see here intermittently very large forces are acting with this particular case. So, in this case you can remove the deeper chip or larger chip from the workpiece after its shearing. Why rotation of abrasive particles in the brush or the medium? If radial force is more than the required one, force required to remove material from workpiece, tau s AP, where tau s is shear strength of workpiece material, AP is the projected area of penetration, and F required is equal to Ft, that is the equilibrium condition. F required depends upon the workpiece material property, and Ft is the force that you are applying. If F required is less than Ft, then what will happen? Material removal will take place. If F required is greater than Ft, no cutting condition will exist. If F required is less than Ft, then material removal will take place because the force that you are applying is greater than the required based on the workpiece material properties. And if F required is more than the what force you are applying, then because it will not be able to shear off the workpiece material, so no cutting condition will exist. So, equilibrium condition is Ft is equal to Fc, that is what is shown over here. How rotation of abrasive particles in the brush medium takes place? The depth of penetration of cutting edge is adjusted by rotation of the magnetic abrasive particle until cutting force required becomes equal to the cutting force available, that is Ft is equal to Fr. That is Ft equal to F required is equal to Ft. F required is equal to tau s into AP, that we have seen. This is the shear strength of the workpiece material and this is the projected area. That is what you can see here. Initial position of the cutting edge of abrasive grade is this one, and final position of the cutting edge of abrasive grade after rotation becomes this. So, really what happens? Finishing of blade bearing by magnetic abrasive finishing process at IIT Kanpur. You can see this is before finishing 596.5 nanometer, surface roughness value was there, and after finishing 86.0 nanometer. This work was done by Mr. Pavan Bashera. He did MTech at IIT Kanpur. Now you can see another case. Before finishing, it is 1024.6 nanometer surface roughness value, and after finishing, it comes down to 82.5 nanometer surface. So there is a drastic change in the surface roughness value after finishing, and surface texture also you can see clearly visible over here and here. So third case where surface finish RA value is 871.9 nanometer this, and you can see the shining of this after finishing, it comes out to be 83.1 nanometer. So you can see in all the cases you are achieving the surface roughness value around 80 nanometer. This is before 577.6 and this is after 84.7 nanometer. So you can clearly see that you can easily finish by MAF process these bearings, etc. Difficulty in surface roughness measurement. As you can see over here, the part or the surface that is to be measured for this bearing is tapered one, and if you use this over here, then all the chances are there that this pin may get broken. This pin may get broken. So one has to be very careful. Details of parameters used during measurement are as follows: sample length 0.8 millimeter, number of samples 5, evolution length 4 millimeter, and speed of stylus. This has to be controlled very carefully for the safety of the stylus. 0.5 millimeter per second, length of stylus 20 millimeter, and tip diameter of stylus 5 micrometer. This is to be carefully noted. Very thin tip is there. Tip angle of stylus is 90 degree. Issue 4, slot in the electromagnet. Electromagnet has a slot along its periphery. Why? What is the optimum number of slot? Now you can see here, this is a slot over here, this is the another slot over here. So magnets have some slots, and as I mentioned earlier that magnetic field concentration is there at the discontinuity, so that these abrasive particles have larger normal force and shearing force wherever you have larger magnetic field concentration. So this is the finite element analysis, simulation solution domain for finite element analysis over there. This was done by Professor S.C. Jaiswal. No machining zone under a slot in the electromagnet. You can see here, this is the slot and minimal machining is taking place. There are the slots, no machining region are there, and at the peaks you have the larger forces acting over there, and so finishing is there. You can see here without slot is this slot is this RA value or R max value. So better, smaller the value, R max value or RA value, better the surface finish. DC magnetic abrasive finishing before MAF, this is the surface roughness, 0.58 is the surface roughness value. This is what you can see here for another case. This is after MAF for this particular case, and after MAF surface roughness has come down to 0.19 micrometer from 0.58 micrometer. Second case, this is before MAF, 0.51 micrometer surface roughness value, and after MAF it has come down to 0.11 micrometer, that you can see here, and this is this, then this one. So all this depends upon number of cycles that you are using for finishing purposes. Best surface roughness achieved was around 40 nanometer in this particular case for the given machining conditions, component and number of cycles obtained by the student. There is another process, very important process, known as magnetorheological finishing process. This process was developed by QED company of USA. This magnetorheological fluid is used for clutches, brakes, dampers, etc. Without using any abrasive particles. The fluid is used over here. But finishing of optical glasses, glass ceramics, plastics and some non-magnetic metals, for finishing them, please note it carefully, non-magnetic metal. Using non-magnetic abrasive particles, this fluid is used for finishing purposes of these type of the materials. So, this is known as magnetorheological finishing. So, we are using magnetorheological fluid along with the abrasive particles for finishing purposes. It has lot of very good application, and QED claimed that they were able to achieve surface roughness on optical lenses which was less than 1 nanometer, and I have already given you one example where we also achieved surface roughness as 0.485 nanometer, that is 4.85 angstrom, by some hybrid process that was developed at IIT Kanpur. Magnetorheological finishing, key features, very high precision finishing of lenses like spherical, flat, aspherical lenses. Surface roughness value as 0.8 nanometer, that is 8 angstrom RA value, and deterministic finishing was obtained by this particular process. Limitations are there. Shape limitation, all different kind of the shapes cannot be finished by this particular process. And then you have another limitation, standard MR polishing fluid are ineffective for polishing hard metal. This is very important limitation of this MRF process, that very hard materials cannot be finished by this particular process. And that was the reason that we at IIT Kanpur developed two other processes. One is known as MRF process and another is known as chemomechanical magnetorheological abrasive flow finishing process, which I have discussed in the lecture. You can see here, this is the lens, this is MR polishing fluid, and this lens is rotating and it is inclined at certain angle. When it is rotating, fluid is moving in this direction, finishing takes place, and electromagnets are there. This is a channel where this is rotating and fluid is moving over there, and this was done at University of Rochester, USA courtesy. This figure is taken from there. Mechanism of material removal. Carbonyl iron particles form a chain-like columnar structure with the application of magnetic field, and they are aligned along the lines of magnetic force. The magnetic force between iron particles provides bonding strength to it, and that is very important because abrasive particles should have the bonding strength through the magnetic particle, that is CIPs. You can clearly see here in this picture the particles which are in contact with this lens. They are the abrasive particles, as you can see, bluish in color, this brown color, and other particles are the iron particles which are bonding them and helping the abrasive particles and applying the force on this particular lens. When these chains have relative motion with respect to the workpiece surface, the asperities on the workpiece surface are abraded due to shearing, plastic deformation at the tips, and these abrasive particles, they are in contact with the lens. Principle of material removal is very simple. This is the asperity on the workpiece surface, and this is the abrasive particle. You can see here abrasive particles are in contact with the workpiece surface over here, and these are the magnetic particles. So, normal force is acting which is responsible for penetration, and Fs is shear force, which is responsible for removal of the material in the form of the micro nano chips. So this is the magnetic particle, these are the abrasive particles. Results of nano finishing of silicon blank by MRF process, that is magnetorheological finishing process. You can see here, this is the unfinished part and surface texture in 3D picture you can see over here, and this is 2D, and the initial surface roughness is 1260 nanometer. This is after finishing. Finished part, you can clearly see the difference between unfinished and finished part, and this is the 2D picture of finished part, and it has come down to 12 nanometer. So you can clearly see that there is a reduction in the surface roughness value by about 100 times. This is 1260 and this is 12 nanometer. So reduction in Ra value by more than 100 times, and this is highly substantial, and this is on the silicon blank, silicon wafer. Nano finishing of free form surfaces is a challenging task. We all know already that free form surfaces cannot be expressed through mathematical equation, and that's why they are known as free form surfaces. We had CNC MRF process setup, computer numerical control magnetorheological finishing process setup. This is the one. We had the CNC machine over which this MRF setup was developed, and you can clearly see over here, this is the one which is going to have, here you are going to have the MR polishing fluid, and here is the workpiece, and it is being controlled through this particular panel, and this is the computer on which you can see the processes and parameters going on. Experimental setup for flat workpieces, you can see over here, this is the picture of the MR polishing fluid over here, shown over here. Here you are going to place the workpiece, 5 is the workpiece, 6 is the workpiece fixture, this is the workpiece fixture, closed view of MR fluid, that is shown over here, and this is the 4 is the permanent magnet assembly is there inside this. As I have mentioned earlier also, you can use permanent magnets in place of electromagnets also, and then you have other components, chain is there, motor is there, AC motor is there, and then you have the CNC milling machine head in which this particular setup has been attached. You can clearly see the different kind of the force magnet is there, field MR fluid is there, so fields etc. are shown over here. Finite element analysis of A distribution and B direction of magnetic flux density is shown over here. Atomic force micrograph of single crystal silicon wafers finished by MRF process. You can see initial surface roughness value Ra 223 nanometer, and after final surface roughness value 140 nanometer using oil based MR fluid. It comes down to 88.5 nanometer when we are using water based MR fluid, and you can clearly see the difference in the surface texture with water based MR fluid and oil based MR fluid. And this is initial Ra value 37.4 nanometer chemical based MR polished fluid is used in this particular case. So you can clearly see the difference in the surface roughness while you are using different based MR polishing fluid. And this is the another one where they have achieved finally 21.7 nanometer with water based MR polishing fluid. So initially it was 223, then they obtained 140, 88.5, 37.4 and 21.7. So all this depends upon for how long you are finishing it and what kind of MR polishing fluid you are using. You can see here this is another example of initial surface. This I have already shown to you, so I need not to repeat it. Finishing of free form surfaces, we have conducted the finishing of knee joint implant consists of femoral and trivial components with a plastic polyethylene insert sandwiched between to restore joint function. Surface roughness of knee joint implant has a significant effect on the force at the connection and reaction of tissues in the joint area and behavior of germs in bone. This is very important because better the surface finish, less will be the pain for the patient and more will be the life of the implant. Whereby abrasion is one of the main causes for failure of knee joints, because over time the continuous movement between the metal and plastic can cause the polyethylene to crack, pit and delaminate. It may also cause microscopic particles to break off, which in turn attack the body's immune system. So, what I mean to say here is that better the surface finish, better will be the performance of knee implants. And you can see here various components of knee implants over there. Motions are there, relative motions are there, and this is being finished as I will show you in the following slide. And here is the relative motion between the two, and because of this relative motion, wear and tear of this knee joint takes place. So you can clearly see the relative motion between different parts of the knee implants, and this is very useful to have high finish or low surface roughness value for the life of the implant. Nano knee joint implant, you can see over here, this was the machine setup that was developed for finishing of this knee joint shown over here. This is the brush which was developed. You can see the enlarged view of this. This consists of ferromagnetic abrasive particles in this particular brush, which is going to finish this knee joint. And you can clearly see the finishing of this knee joint taking place over here with the help of this particular brush. And it can be controlled with the help of the computer. This forces etc. they can be controlled, magnetic field, although we have used here permanent magnet, but if we are using electromagnet, we can externally control the magnetic field, and if we can control the magnetic field, forces can be controlled working on it. Now this is very important to note that orthopedic doctors, they suggest that around 100 nanometer surface roughness value of knee implant is good enough, but we have, as I have mentioned earlier, we have been able to achieve as good as around 30 nanometer surface roughness value. It can be further reduced, and better the surface finish, better will be the life and performance. So we have achieved between 29 and 56 nanometer surface roughness value in different phases of this particular knee joint. Photograph of knee joint implants. You can see here, this is the initial knee joint implant. There is no reflection of IIT, bark, etc. on this particular face, but finished surface with chemical added MR fluid. You can clearly see the reflection of IIT and bark on this same face after finishing. And this is finished with water waste, and it gives a better reflection, better shining on the finished surface of the knee joint. Some problems are there. It is taking long processing time because you are finishing it a very small area, and it takes lot of time in finishing it. Non-uniform finish on different faces of the knee joint, as I have shown to you, and you can see here, this is the flat, but other face, this part is not flat. This is, you know, maybe free form surface or in curved surface is there. So at different faces, different surface finish is obtained. That's why I had written there The surface finish obtained in different parts, it lies between 29 nanometer to 56 nanometers. Now, what is the solution that we will see later on? Can you finish all the 4 phases in one go, that is simultaneously? Yes, we can finish all the 4 phases in one go by using other processes that I will tell you later on. Nano finishing of silicon blank by MRI process, you can see this is the rough part and this is the finished part, and there is clear reflection of this nib and pen over this surface. Initial surface finish was 1.26 micrometer and that is 1260 nanometer, and it came down to 14 nanometer. So, approximately 100 times reduction of the surface finish, and these are the different machining finishing conditions. This is the initial surface roughness and this is the final surface roughness of 14 nanometer of this silicon blank, that is what you can see over here, and this is the initial surface. Optical views of finished surface, you can see I have shown to you. This is a mirror image of IIT Kanpur on the silicon wafer, you can clearly see, and DST image of polished surface under sunlight. This is it is reflecting image of book is there and this is getting reflected over here. This is the reflection. And finished silicon substrate with brass cylinder, and another view of the thing. How to minimize reduce finishing time? Why to finish by spherical brush which covers very small area in one pass? These are some of the questions. Can we finish all the 4 surfaces in one go? Can we use abrasive flow finishing or magnetorheological abrasive flow finishing so that all the 4 phases are finished at the same time? Total time taken is substantially reduced when we are using one of these processes, and you get equally good surface roughness value. Why to stop at knee joint nano finishing? Very important question for the doctors as well as for the engineers. Why not other implants also? There are so many, hip joint is there, knee joint is there, fingers are there, so many implants are there in the human body. Why not to finish them so that you get better performance of artificial implants and better or comfortable life for the patient and longer life of the implants. Yes, we plan to go further at IIT Kanpur. Conclusions: MAF process is simple and applicable for nano finishing of flat, cylindrical and other shapes. Pulse MAF gives better performance than DC MAF, but it normally takes more time compared to DC MAF. We have already seen the pulse MAF, because in pulse MAF you have the off time where no finishing is done, only under on time the finishing is being done. So it takes longer time. Magnetorheological finishing process developed by QED company of USA uses magnetorheological fluid for finishing different types of components. MAF and MRF processes are useful processes for micro nano finishing of different types of components, including free-form surfaces. And I can comment over here that for free-form surfaces, abrasive flow finishing, magnetorheological abrasive flow finishing, they are more efficient processes. However, you can use MAF and MRF also, but they are not so efficient. Thank you very much.